Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today, path with maximum probability, Leetcode 1514. In this problem, we are given an undirected weighted graph of n nodes. So that means we can go in either directions. Zero index, that means nodes are labeled from 0 instead of 1. Represented by an edge list where edge I is equal to AB is an undirected edge connecting two nodes A and B with a probability of success of traversing that edge succProb I. Then we are also given start and end nodes, and we have to find the path with the maximum probability of success to go from start to end and return its success probability. If there is no path from start to end, then we should return 0. Our answer will be accepted if it differs from the correct answer by at most 1e to the power of -5. Because comparing doubles may result in rounding errors. So that is why this 1e to the power of -5 allows for a small margin of error. Then in example 1, we are given a graph with 3 nodes, 0, 1 and 2, with 3 edges with success probability 0.5, 0.5 and 0.2. And then they have given start node as 0 and end node as 2. So if we go from 0 to 2 by this edge, probability of success will be 0.2. And this is not the maximum probability, because if we go from 0 to 1, that will give us probability 0.5. And then when we go from 1 to 2, it will be 0.5 into 0.5, that is 0.25. So this path with probability of success equal to 0.25 gives us more probability of success compared to other path. So our answer will be 0.25. Also, we know that probability is a measure of likelihood that an event will occur. It ranges from 0 to 1. So 0 implies the event is impossible and 1 implies that the event is certain. And 0.5 implies that there is a 50% chance of success. For example, traversing the edge 0 to 1, the probability is 0.5, right? And when we combine the probabilities for individual events, that means one event does not depend on the other event, then probability of both events occurring is the product of their individual probabilities. So that is why when we go from path 0 to 1 and then from 1 to 2, we combine the probabilities by multiplying. So this was our quick probability primer. Now in terms of solution, if we look at this problem carefully, it is very close to Dijkstra's shortest path algorithm. We know that Dijkstra algorithm is a single source shortest path. So we start from a source vertex and then find the shortest distance from the source node to remaining nodes or the destination node in the graph. And here also we are given a source node, right? Second property we can see, like instead of shortest path, we want the maximum probability. So again, both requirements are greedy. At one place we require the shortest path and here we require the maximum probability. So we can actually use Dijkstra algorithm to solve this problem, but there will be some differences. Dijkstra algorithm finds the shortest path. This will find the maximum probability. The distance array that we use in the Dijkstra algorithm has initially all the values set to infinite because we have to find the minimum value. But here we will set the minimum value to 0 because probability can lie between 0 and 1, right? So we can choose the minimum value as 0 and then try to maximize it as the algorithm proceeds. And third thing is, like when we are actually doing the Dijkstra algorithm, we are adding the distances basically. But here we will be actually doing the multiplication, because when we are combining the two probabilities, we have to multiply. Also in a normal Dijkstra algorithm, because we are finding the minimum distance, we use min heap. But because we have to now find the maximum probability, we will use the max heap. So now let's quickly see it in action. So we are given this graph, and first thing we will do is we will actually build the adjacency list. So because it's undirected graph, we can see that the adjacent elements for 0 will be 1 and 2. Then for 1 it will be 0 and 2. And for 2 it will be 0 and 1. Then when we start the Dijkstra algorithm, generally we have this distance matrix, but here we can actually create a maximum probability matrix. Now we start the Dijkstra algorithm by pushing the source or the start node on the max heap with the maximum probability. And what will be the maximum probability of reaching the source node from source node when we are actually starting the algorithm? It will be 1.0 or 100%, right? Because we are already at the start node. So we will set maximum probability of 0 to 1.0 and add probability 1.0 for node 0 to the max heap. And now we start the iteration until our max heap is empty, or we find a destination or end node. So we pop out the node with the maximum probability from this max heap and try to update the probabilities of its neighbors. So we only have one node on the max heap, that is our source node or the start node. So we pop it out and now we look at its neighbors for edge relaxation. what do we mean by edge relaxation? So edge relaxation refers to the process of updating shortest distance to a node if a shorter path is found via another node. Suppose we are trying to reach from node U to V through some another node W. For example, we are trying to reach 0 to 2 through node 1, for example. Then in case of normal Dijkstra algorithm, if we find the path from U to V through this node W, which is actually shorter than the previously known path till V, then we actually update the distance V to this shorter value, and this is what we mean by edge relaxation. So in our case, this edge relaxation will mean that we will set the maximum probability, right? So for example, we know that we can reach from 0 to 2 with probability 0.2, but later on in our algorithm, we will relax the edge at node 1. So because of that, we will get the maximum probability of reaching node 2 to 0.5 into 0.5, that is 0.25, which is larger than current value of 0.2. So we popped out source node 0 with probability 1.0, and we now relax the edges at node 0. So we can see from the adjacency list that its neighbors are 1 and 2. So now we calculate the probabilities to reach node 1 and 2 through node 0. So we calculate the probability to reach node 1. It will be 1.0 into 0.5 equal to 0.5, because the probability to reach node 0 was 1.0 that we got from the max heap, right? And probability to reach node 1 is equal to 0.5, which we got from the adjacency list, right? And because to combine the probabilities, we have to multiply. We will multiply both the probabilities and get 0.5 as our answer. We also set this value for node 1 in maximum probability array. That is, we set maxprob1 equal to 0.5, and we also add an entry to max heap as 0.5 for node 1. Similarly, we calculate the probability to reach node 2 through node 0 as 1.0 into 0.2, that is 0.2. So we set the value for node 2 in maximum probability as 0.2 and add an entry to max heap as 0.2 for node 2. And now we are done with all the adjacent elements of node 0. So we will extract the node with the highest probability again, which is 0.5 for node 1. So we relax the edges of node 1. Node 1 has two adjacent elements, 0 and 2. So we calculate the probability to reach node 0 through node 1. It will be 0.5 into 0.5 equal to 0.25. Because we got 0.5 from the max heap, that denotes the probability to reach node 1 from node 0. And then we multiply it with 0.5 that we get from edge between node 0 and 1. So that is why it will be equal to 0.25. But the probability to reach node 0 from node 0 was already 1.0, as we can see it in the max probability array. So we will ignore this value of 0.25. And now we go to node 2 and try to relax the edge between node 1 and 2. We calculate the probability to reach node 2 through node 1 as 0.5 into 0.5 equal to 0.25, which is more than the current probability of 0.2 to reach node 2. So we will update the maximum probability of node 2 as 0.25 and also add an entry to max heap for probability of 0.25 for node 2. So now we have two elements in it, 0.2 with node 2 and 0.25 again with node 2. And we again extract the node with highest probability, and we get node 2 with maximum probability of 0.25, and this is equal to our destination element. So we terminate and we return the maximum probability as 0.25 that we got from max heap, and that is our answer. So now let's jump into the code part. So first thing we will do is build the graph. We will use the adjacency list representation. So we will create the map where key will be the vertices and value will be the list of probability edges. So let's define the probability edge class. It will contain the vertex and corresponding probability value for the edge, similar to weight in the graph, right? So let's define the constructor as well. So now we will add all the edge information to the graph. So we'll loop over all the edges. So let's define the node U as edge 0 and node V as edge 1, and our probability will be equal to succProbability of I. And now we will put the node in graph. So to avoid if then else condition to check if node exists in the graph or not, or in the map or not, we can actually use graph.put if absent. So if the value is absent, then it will automatically add a new list to the graph. Internally, most probably it must be doing if then else condition, but it makes our code a bit cleaner. And now we will add node v to the adjacency list of u and vice versa. We will get the adjacency list for node u and add probability edge for node v. We will do the same thing for node v as well. So now we will start our Dijkstra algorithm. So first thing for that we will need is a max heap. In Java we use priority queue for that. It returns a node with the highest probability. That is, it always prioritizes a node with highest probability. So we will use double dot compare for that and pass in the probability of b before a. Let's rename it to prob to keep the code smaller. Now we push start node to the queue with probability 1.0, indicating the certainty at the start because we are already there. We will also define our max probability array similar to distance array in Dijkstra algorithm and set the max probability value for start equal to 1.0 here as well. So now we will run the loop till our priority queue is not empty or we have reached the destination element. We pull out the element with highest probability from the max heap using pq.poll. We get the corresponding node and corresponding probability value. And we check if node is equal to our destination element, that is end node. Similarly, I should use variable start node instead of start here. Okay, so if node is equal to end node, then we will return the probability we got from the max heap. Otherwise, we will now try to relax the edges around the current node. So we will go through all the neighbors of current node. So again, because we are representing graph as map, we can use get or default method instead of checking if node exists in the graph or not. So if it doesn't exist, in that case, we can return an empty list. So we get next node as any.vertex, our edge probability as neighbors probability. Our new probability to reach this neighboring node through current node will be multiplication of probability that we get from max heap into the edge probability. Now we check if new probability is greater than maximum current probability of the next node. Then we will relax the edge. So that means we will set maximum probability of next node to this new higher probability and we add new element to the priority queue as well. We will pass next node and new probability. But if in the end we couldn't find anything, then we will return 0.0. So that's it. Now let's run this code. This should be edge 1. Let's run this code again. It should be current vertex, current probability. Let's run it again. Why am I getting 0 here? I think I found the issue. The issue is with the constructor. I should have used probability here instead of prob. So that was a silly mistake. So now let's run this code again. Cool, let's submit this code. Awesome. In terms of time complexity, it will be O of E log V, where E is number of edges and V is number of vertices. Because when we build the graph, that takes O of E time, right? Because we are looping over this edges array. And when we are running a Dijkstra algorithm, we are adding the vertices to the max heap E number of times because it's proportional to the adjacency list, right? And even though the same vertex is added multiple times, number of entries in the max heap will be proportional to V only. Also, adding or removing max element from max heap takes O of log V time. So, overall the time complexity is O of E log V. And in terms of space complexity, it will be O of E plus V because we are storing graph as an adjacency list where keys are all the vertices, so that's where V comes from, and all the edges are stored as values, so that is why it will be O of E plus V. I hope this video was useful to you. If it was, please like, share and subscribe. If you have any questions or suggestions, please write in the comment below. Have a nice time. Thank you.